Previously, we talked about the sequential search, which basically goes through a collection one element at a time and checks each one to see if it's what we're looking for. The advantage of the sequential search is that it works with any data regardless of its format or how it's stored. The downside of the sequential search is that it scales in how much work it does with the number of things you have. Basically, it's not all that efficient. This is where the binary search comes in. So if your data happens to be sorted, you can do a much better job of looking for things. And the example that I often use for this is looking for things in a telephone book. The sequential search is what you would have to do if you were looking for things by the number. So if you have to try to look up a person's name based upon their telephone number, and you have a telephone book to do this with, you would have to go through each and every listing and check to see if it was the right number until you found the right one. It's not very efficient, and no one wants to do it that way. On the other hand, if you're asked to look up someone's phone number by their name, well, because it's sorted by that information, you can do this much more quickly. And what you do as a human is actually pretty close to a binary search. The way the binary search actually works is it looks in the middle of the, we'll use an array because we need something that has random access here. It looks in the middle of it and it checks, is this the value that I'm looking for? Now, if you're really lucky, maybe it is, but more than likely it's not. And then you do a comparison and see whether the thing you're looking for is less than it or greater than it, in which case it will either be off on the left side or it'll be on the right side. And by doing that, you have literally cut away half of the data. And then you go to the middle of what's left and you do the same thing over and over again. So the binary search winds up doing this repeated cutting in two. So we want to write a binary search. Now we're going to write binary search in two different ways. The first way that we're going to write it is an imperative style that uses a while loop. Def binary search. And this version we pass in our array of ints, and the value that we're looking for, which is an int, and this is going to be kind of an index of. We're going to give back the index of the thing that we are looking for. As with our previous index of, if it doesn't find it, it'll return -1. Okay, so the first thing we're going to do is we're going to create some vars that represent the range that we're searching in. So the first index that we're looking at is 0, and then we're going to have an end value that is the length of the array. Note that that's actually one beyond the last element. That's intentional, it's kind of customary, and it helps with the math doing the integer division. And now I'm going to have another var that is the midpoint of those two. Okay. So now I want to keep going as long as I need to keep searching as long as two things are true. One, end has to be greater than start. If end's not greater than start, we have nothing in our range and we clearly didn't find it. And I want to say that we haven't found it yet, and we're checking that midpoint. If a sub mid is not equal to the value that we're looking for, then we want to keep going. So what do we do inside of here? Well, we know it's not equal to, because if it had been equal to, we would have broken out of the loop. So that means it either has to be less than or greater than. So we're going to say if the value that we're looking for is less than a sub mid, throw in an else there. If it's less than, well, that means that it has to be on the left side, and I am going to set end equal to mid. Okay. Remember, end, the high end is exclusive. Just like here, that wasn't a real index in the array. We have verified that it is not located at mid, it is less than that, so that bounds is exclusive, and we can set it equal to mid. On the other hand, if value is greater than the value that in the middle that we're looking at. Then we want to set start equal to mid plus 1. And the plus 1 is because the start side is inclusive, and we want to skip over the thing that we verified isn't our answer. Now that we have a new end and a start, we should recalculate mid. And there we go. That will keep looping until either it finds it or the range gets down to 0. And so at the end, we can check. We can say, well, if end is greater than start, that means that we found it and mid is our value. Else we didn't find it, and we'll give back -1. We should try running this. See if it works for us. Okay. So let's load in our file. And I want to call binary search on the array. Now this only works if this is sorted, so I have to put these values in sorted order. I'm just going to go through and make them consecutive values. I didn't have to. I could have put spaces in there, but it in some ways doesn't matter, other than making it easier to check the accuracy of my answer. And let's say I'm going to check for the value 3. Actually, no, let's go for 8. Sure. And I get the index 7, which is what I should, because the 1 is at index 0, 2 is at index 1, etc. So 8 should be at index 7. What if instead I was looking for 10? That should give me a -1 because it does not occur. So we have a working binary search, but this is an imperative binary search. Turns out that binary search can be expressed very nicely, in fact, in a nicer way, using a recursive function instead. So we'll come back and we'll do that in the next video.